A barrel full of water has a spigot near the bottom at a depth h beneath the water surface. How fast is the water coming out of the spigot? Assume that the cross-sectional area of the spigot is much smaller than the area of the top of the barrel. So what that last bit means is that, remember our continuity equation. A1 V1 is equal to A2 V2. So if this area, we'll call this A1, is really large compared to this area, we'll call that A2, then that means this speed V1 is going to be extremely small compared to this speed V2. So small, if this is large enough, it'll be so small that we can just neglect it. We can assume that the speed here, the water surface moving down, would be approximately 0. So we will operate under that assumption, and we're going to apply Bernoulli's equation. So we need to pick 2 points of interest. I'm going to pick water surface and the opening of the spigot. If we want to know how fast the water is moving out of the spigot, it makes sense that that's one of the points we want to know about. On the other hand, we need to know another point, or we need to use another point that we know about. So if we use something up here exposed to air, that's a nice easy one to use. We know that it's just going to be atmospheric pressure, and we know what the height is according to whatever we choose for our coordinate system. So let's call this down here point 1. This up here we'll call point 2. We'll also say that we're going to call this down here our origin. So y is equal to 0 down here. That means that up here this would be y is equal to the height h. That's the distance between the water level and the spigot. So Bernoulli's equation. Let's start off with 1. So absolute pressure at point 1 plus the density times g times vertical coordinate, vertical position y1, plus 1/2 the density times the speed squared. That's equal to all that stuff now for point 2. Absolute pressure at point 2 plus the density times g, position y2, plus 1/2 rho v2 squared. And we said, since this area up here is so much larger than the area down here, we're going to say that that is approximately 0. We also said that we're going to call this our origin down here, so y1 is equal to 0. Okay, now what do we have left? Think about what P1 is. Even though this water is moving out through the spigot, it's still exposed to still air. So the air is not moving here. So it's still exposed to this air, so this is going to be atmospheric pressure. P2, up here at the top. The top of this tank is open. Then, of course, this is also going to be atmospheric pressure. Since P1 and P2 are the same, those will cancel each other out, because you have one atmosphere here, one atmosphere here. those will cancel, and we're left with just 1/2 the density times V1 squared is equal to the density times G. We said Y2 is equal to H. Now our densities cancel. We're solving for V, so take the 2 over, and then we take the square root. So V1 is equal to square root of 2 GH. Now, if we were to not think about the fluid and just think about taking a mass, a ball or something, you drop it from a height h, you would get the same thing for the speed. Because remember, this is energy density, this is energy per unit volume you can think about. So you get the same thing you would if you were to just drop something. Now, clever question would be, what happens if we take this spigot and we angle it up so that the water will shoot straight up in the air? How high will the water go? Well, if it's going this high, you can use conservation of energy. Treat it like a projectile after it leaves the nozzle. You would see that it's going to go exactly to the height of the water level if it were to shoot straight up. Another question that could be asked is, if we don't have this at an angle, the water is going to come out and it's going to act like a projectile. So we could ask, how far does the stream of water go before it hits the ground or something? Maybe this is up on a table. See how far it goes before it hits the ground. So then you would do this to find the speed. That's horizontal. So then you go back and you use the kinematic equations of motion to describe the motion of the water after it leaves the tank. Now, for part B of this question, it asks, does the result change if the cross-sectional area of the spigot is comparable with the area of the top of the barrel? So, what if we say that this area is not large enough to forget about the speed? Well, in that case, what we would have to change is we can no longer say that V2 is equal to 0. So then how would we get V2? Well, we have to go back and we have to use this now. So, continuity equation. Area 1 times V1 is equal to area 2 times V2. So that means that we would have to say V2 is equal to area 1 V1 over area 2. We would plug this in right here for this V2, and then we would have to solve for V1. So just be a little bit more complicated when we try to solve for that, because at that point we're going to get, so let's write that down, you would end up with 1/2 density times V1 squared is equal to this part here, which is density times G times H, plus 1/2 density, and let's plug in A1 over A2. Remember, all this is squared, so A1 squared over A2 squared times V1 squared. So our densities will cancel. Oops. Densities cancel. And we could take this across, and what we end up with is we can take this over, factor out the v1. So we have v1. When we solve this, v1 is equal to square root of, we'll have a 2 gh in the top, and then in the bottom we're going to end up with a 1 minus a1 squared over a2 squared. Should look like this. You should be able to work through the algebra there. Take this term over here, factor out the v1 squared, then divide by what should be 1 minus a1 squared over a2 squared, and then we're going to take the square root to get just the v1. So this is what it would look like if those areas are comparable, and you cannot just forget about the speed v2.